Well, solutions for problems of rolling. We have rolling bodies. The bodies which can roll can be called rolling bodies. The body which rolls can be called rolling bodies, but it has to obey the conditions for rolling. One of the condition for rolling is V is equal to R omega. This condition comes after equating the velocity of this point with 0. The surface that is horizontal is fixed. Fixed horizontal surface. Therefore, for rolling, velocity of the lowest point of the body must be equal to velocity of contacting point of the horizontal surface. Since the horizontal surface is fixed, the lowest point velocity of the rolling body should be 0. When the velocity is 0, the body is said to be pure rolling. This is the center of mass, this is the angular velocity, this is the linear velocity of the center of mass. With this diagram, we can draw the velocity of the point with respect to center of mass and bring the velocity of the center of mass to the same point. And this 2 Vc minus Vpc is equal to Vp I cap. When this velocity is 0, then we can get Vc and Vpc. These two velocities must be equal and opposite. Center of mass velocity must be equal and opposite to the velocity of the lowest point with respect to center of mass of the rolling body. Vc is equal to V, Vpc is R omega. So this is the condition. If you differentiate both sides, we are getting dV by dt is equal to R d omega by dt. This is the velocity of center of mass. This is the angular velocity of the rigid body. This is another condition. If the center of mass moves with acceleration AC is equal to A and the rigid body has angular acceleration alpha, for rolling we can write A is equal to R alpha. For rolling, A is equal to R alpha. Acceleration of the point P is equal to acceleration of the point P with respect to C plus acceleration of C. We are retrospecting the kinematics of rolling. This acceleration has two components, APC tangential, APC radial. We have discussed this matter in the kinematics of rolling, the last chapter, plus AC. This gives us acceleration of this point P with respect to ground. APC, this is the center of mass, APC tangential, this is APC radial. This is equal to r omega square. This is equal to r alpha. We have discussed about it already. APC is equal to r alpha plus, in which direction? Minus I cap. APC along radial direction is r omega square in upward direction. Therefore, the net acceleration of this point is equal to r square alpha square plus r square omega 4. That's very interesting. And here we have done something we have missed. AP is equal to APC plus AC. APC has two components. APC tangential is minus r alpha. APC radial is r omega square. This we have forgot to include. AC, acceleration of the center of mass, is A I cap. So plus A I cap. Therefore, AP can be written as A minus r alpha I cap plus r omega square j cap. This is the APX plus APY. Here one very interesting thing we can derive, we can conclude that acceleration of this point is not 0. However, acceleration of this point along the x direction, along the horizontal direction, along the tangential direction is 0. Acceleration of this point P is equal to A minus r alpha square of this plus r omega square square of this square root is not equal to 0, because A minus r alpha is 0, AP is equal to r omega square for pure rolling. Acceleration of this point P is not equal to 0. However, acceleration of this point P along which direction? Along x direction, that is equal to A minus r alpha is equal to 0. And this gives us A is equal to r alpha. Why acceleration of this point P along x direction is 0? Because x direction is known as tangential direction. This is the tangent and this is the normal. Along the tangent, the acceleration of this point P with respect to ground is A minus r alpha, and the rate of change of the speed of the particle is known as tangential acceleration. The rate of change of the speed of the particle V is equal to r omega, this is correct. dV by dt is r d omega by dt, this is also correct. dV by dt, there is a little confusion. dV by dt is the acceleration of the center of mass, but not acceleration of this point P. Acceleration of this point P is equal to A minus r alpha I cap plus r omega square j cap. Now question arises, why this will be 0? This is the question I posed. Why should the acceleration of this particle, acceleration of this lowest point, a rate of change of velocity of the lowest point along this direction will be 0? That is an interesting question. Let me continue the discussion for rolling V is equal to R omega. This is easier to understand, but this is not so easy to understand why A is equal to R alpha. But if we follow logically, acceleration of this point is equal to acceleration of this point with respect to center of mass plus acceleration of the center of mass. And this has two components, APC tangential, APC radial. Tangential component of acceleration is equal to R alpha in negative x direction, and the radial component of the acceleration of the point P with respect to the center of mass is R omega square in upward direction. And if you add the acceleration of the center of mass with this, you are getting the net acceleration of this point P with respect to ground. In this way you are getting this. A minus R alpha is 0. This is because V equal to R omega, derivative of V, that is the acceleration of center of mass, derivative of omega, that is the angular acceleration of the rigid body. So A minus R alpha will be equal to 0. When you put at 0, then acceleration of the point P will be equal to, this factor will be 0, will be equal to R omega square j cap. So it is interesting to note that the lowest point will accelerate not along the tangential direction, not along the horizontal direction, but along the vertical direction towards the center of mass. Or we can say with respect to center of mass, this moves in a circular path. Therefore, its net acceleration will be equal to its acceleration towards the center, that is radial acceleration you can say. So that is an interesting question. A minus R alpha will be equal to 0 because A is equal to R alpha. Anyway, we are getting this answer. AP is equal to R omega square j cap is not a null quantity. However, APX is equal to 0. APX is equal to 0. APX is equal to 0. AP along tangential direction or AP along x direction is equal to 0, but AP axis of this point as a whole is not equal to 0. This is the idea. Well, so these are the kinematical matters we are discussing. This will be helpful for writing or solving the problems of rolling. In addition to the kinematical equations for rolling, you have to write the dynamical equations. Let us discuss the dynamical equations through particular problem. The problem is you take a rolling body and apply force horizontally at the center of mass. Such that the body will roll. Say this body is a disc. We can find the acceleration of center of mass, angular acceleration, and frictional force required for rolling. Now question arises, why should friction be needed for rolling? Let us solve the problem by using our kinematics and dynamics. So we have our dynamical diagram, that is called free body diagram. When you make the body free, you can see that, or you can show that the horizontal surface is pushing the body up, that is called normal reaction. And frictional force, we do not know. It may be backward, it may be forward. When we are not sure about its direction, we have to assume the direction and magnitude be, and this force of friction, the static force of friction, because for pure rolling there is no relative sliding. Therefore, we have to give a suffix s. S stands for statics, static, not static, static, static friction, not kinetic friction, but not kinetic friction, because for rolling, relative velocity between these two contact points is 0. Therefore, no slipping will be there. Since the static friction prevents whereas kinetic friction opposes, there is a difference. The kinetic force of friction cannot prevent, it may oppose the relative sliding, but static force of friction prevents the relative sliding. During rolling, Fs may act, but not Fk. Well, we have chosen the magnitude and direction of the force of friction, a normal reaction, the applied force, and the gravity. Under the action of this four forces, the body is rolling with center of mass acceleration A and angular acceleration alpha. You take A in this way, alpha in this way, you can write A is equal to R alpha. But if you take A in this way and alpha in this way, you have to alter. You cannot write A is equal to R alpha. This will be wrong, because this point velocity will be equal to velocity of this point with respect to center of mass, or acceleration of this point with respect to center of mass, that is r omega square, and radial component and tangential component will be equal to r alpha, and then you can write F is equal to A plus r alpha I cap plus r omega square j cap. With this assumption, this is the acceleration of this point. With this assumption, acceleration of this point will be A minus r alpha I cap plus r omega square j cap. Here you can write this will be 0. Can you write here this will be 0? Let us see. Velocity of center mass is V, angular velocity you have taken in anticlockwise manner. So here velocity of this point is equal to velocity of this point with respect to center of mass plus velocity of the center of mass. So Vp is equal to Vpc plus Vc. Vpc is equal to r omega in positive x direction, and Vc is equal to V I cap. So you are getting V plus r omega into I cap. That is this point's velocity. Rate of change of, well, just make it scalar, Vp equal to V plus r omega. Since this is rolling over this fixed surface. This point velocity must be 0. Vp must be 0 for rolling. When Vp will be equal to 0, then you can write 0 is equal to V plus R omega and differentiate both sides with respect to time t once to get 0 is equal to dV upon dt plus R d omega upon dt. This is the acceleration of the center of mass because V is the velocity of center of mass, magnitude, plus R into this is the magnitude of angular acceleration. So A plus R alpha will be equal to 0. When you take this assumption, then you can write A plus R alpha will be equal to 0 for pure rolling. If you take this assumption, you can write A minus R alpha will be equal to 0, or A is equal to R alpha. It is kinematics for rolling. If you take this assumption, you have to write A is equal to minus R alpha or A plus R alpha will be equal to 0. Let us now write the dynamical equations. Newton's law of translation or force equation. The net force acting on the object along x direction is equal to mass times its acceleration of its center of mass along x direction. Net force acting on the object along x direction is equal to one force along positive x direction, another force static friction along negative x direction is equal to m into acceleration of the center of mass I have assumed along positive x direction. Equation number 1. Next, the net force along y direction is equal to m into its center of mass acceleration along y direction. Along y direction, one force is acting up, that is plus, and the force is acting down, that is minus, is equal to m into ay. Since the center of mass moves along a straight line and axis of the center of mass or velocity of the center of mass, or you can say velocity of the center of mass along y direction is equal to 0. The derivative of its velocity along y direction with respect to time will be equal to 0. Therefore, the center of mass acceleration along y direction will be equal to 0. This is not moving along y direction. Since ay will be equal to 0, n must be is equal to mg. Equation number 2. Two force equations. We have a torque equation. The net torque acting on the object, the frame is center of mass in this method. About the center of mass axis, this cannot produce a torque because it passes through the center of mass. This cannot produce a torque because normal reaction passes through the center of mass. Only the torque can be produced by the static friction. The static friction produces a torque in which direction? In clockwise direction. Let us document these force equations in this side. F minus Fs is equal to ma. This force equation. N is equal to mg. Next, let us write the torque equation with respect to center of mass. The torque is tau c, that's equal to ic into alpha, where tau c is equal to sum of torque of this force and this force. These two forces pass through the center of mass, therefore they cannot produce a torque about the center of mass. Torque is produced by the frictional force only about the center of mass. That is equal to Fs into r, in which direction? Clockwise or minus k cap direction. This is torque. Torque of the forces will depend upon the reference point, whereas the angular acceleration doesn't depend upon the reference point. That is an incredible, interesting concept. The torque experienced by the rigid body depends on the reference frame, but its angular acceleration does not depend, because angular acceleration is equal to torque upon the moment of inertia. Torque about any point upon the moment of inertia about that point, it is a constant quantity. And that constant quantity is the angular acceleration. This method you have taken the reference point center of mass. These two forces pass through the center of mass, cannot produce a torque about it. But if you take the reference point, this point, lowest point, or any point on the ground, this frictional force which can produce a torque about the center of mass cannot produce a torque about any point on the ground or about the lowest point. And the gravitational force will produce a torque in clockwise direction about this point. Normal direction produces a torque in anti-clockwise direction about this point, and both the torques will be equal and opposite. When you solve the problem with respect to ground frame, maybe after this example, I may explain the theory of that. How to solve the problems of rolling? How to solve the problems of rolling with respect to the ground frame? That's called ground frame method. But this is solutions for problems of rolling. Solution number 1, we are following the center of mass method. About the center of mass we are taking the torque, not about the ground frame or ground point. However, we are writing the Newton's equations with respect to ground. Newton's equations are force equations. This is also Newton's equation. This is also Newton's equation. But Newton equations for translation or force equation you are writing with respect to ground, and torque equation you are writing with respect to center of mass. In another method, we can write the torque equation with respect to a fixed point on the ground. That's called ground frame method. But let me solve this problem first by using center of mass method. Well, and alpha is equal to, we have taken alpha in clockwise sense, so minus k cap you can write. This gives us minus Fs into r k cap is equal to minus alpha k cap. So we are getting into IC. If it is a disk, the moment of inertia about the center of mass, axis, that z axis, is equal to mr square by 2. So we can just write Fs into r is equal to mr square by 2 alpha. This gives us Fs is equal to mr by 2 alpha, equation number 4. So we have one torque equation two force equations, one kinematical equations. So, force equation, torque equation, kinematical equations, three concepts we are using, and we are getting four equations. We have to solve all these equations now. So, Fs is equal to m r alpha by 2, that is equation number 4. A is equal to r alpha, equation 1. You substitute A is equal to F minus Fs by m from equation 2 in equation 1, and alpha is equal to 2Fs by mr from equation 4 in equation 1. To get F minus Fs is equal to Fs, and this gives us the magnitude of the static friction required for pure rolling, F by 3. Answer. Once you get F, a frictional force Fs into 2 by mr, this is the alpha. And substitute Fs is equal to F by 3 by mr, so 2F by 3 mr. Answer. So, we are getting alpha. And acceleration of the center of mass, from equation 1 you can get A is equal to r alpha. So, this will be, by substituting alpha here, 2F by 3m. Answer. Sometimes they may ask you, find the minimum coefficient of static friction. Find the minimum coefficient of static friction required for pure rolling. So, for this we have to utilize this equation while we are writing the equation of friction or law of friction. For this, it will write law of static friction, which states that static friction is less than equal to coefficient of static friction mu s times the normal reaction. This is another equation, that is fifth equation. And what is N? N is equal to mg. Using these two equations, we can get Fs is less than equal to mu s mg. But what Fs we have calculated? Substitute here. That is F by 3 is less than equal to mu s mg. This gives us mu s is greater than equal to F by 3 mg. So, minimum value of mu s required for pure rolling is equal to F upon 3 mg. So, this problem we have solved by using the center of mass method, taking the torque of all forces with respect to center of mass. We are able to solve the problem. However, kinematics of rolling, this equation is common for both the procedures. Newton's law of translation or the force equations are common for both the procedures.